Section 11.1 begins the chapter on sequences and series. So 11.1 is about sequences. Hopefully you remember some sequences from pre-calculus, but let's remember that a sequence is a list of numbers written in a definite order. So we tend to start with A1. We don't tend to. It's normal practice. A1, A2, A3, A4, it's literally A sub 1, etc. And then you have A sub n somewhere in here. And it might keep going, it might stop. So if it stops here, it's called a finite sequence. And if it continues, it's called an infinite sequence. Some important things to note is that A sub 1 is called the first term. A sub 1 is always our first term. A sub 2 is the second term. A sub 3 is the third term. A sub n is called the nth term. So we often decide this is what the pattern would look like, and we can find A sub n, and that would be our nth term. In this section, we're looking only at infinite sequences. So when you have A sub n, that's your nth term, and then there will always be the one after A sub n plus 1. It looks like this, A sub n plus 1, and that's the n plus 1th term. So we talk about what happens in the next term. So these are called one-to-one because you notice every integer has a term. So we have a first term here and a second term, A sub 2, A sub 3. So the integers all have terms. And I think that's the beginning of your sequence. Notation-wise, we have A sub 1, A sub 2, A sub 3, A sub 4, ... My ... won't work. ... And the dots just mean continuing in the same pattern. You need at least, I would say usually 3, maybe 4 terms in order to establish notation. Just be sure your A sub 1 comma looks like a comma, not A11. A sub 1. The second way we have notation is A sub n. And so it'll probably give a formula there. And then the last one is A sub n, and we go from n equals 1 to infinity. So those are the basic notations that we have. I think this section is easiest to just work through some examples with you. So I'm going to move to the exercises and do some of them. So I'm on page 704, and it's exercises 11.1, and I'm going to do some of the even ones with you. I think your exercises and your homework are mostly odds. I might pick up some of them if they're interesting. So if we look at number 4 says A sub n equals n squared minus 1 over n squared plus 1. And that's the way they define the sequence, and the directions say list the first 5 terms. So notice here we have A sub 1. 1 takes the place of n. 1 takes the place of n. So we're going to put a 1 everywhere we see an n. We say 1 squared minus 1 over 1 squared plus 1. 1 squared minus 1 is 0. 1 squared plus 1 is 2. And 0 over anything is 2. Similarly, A sub 2, we're going to have 2 squared minus 1 over 2 squared plus 1. So we have 4 minus 1 is 3 over 4 plus 1 is 5. A sub 3 is 3 squared minus 1 over 3 squared plus 1. So your sub, A sub n, that value gets plugged in for n into the equation. 3 squared is 9, so minus 1 is 8, and plus 1 is 10, and this reduces to 4/5. A sub 4 is 4 squared plus 1. Sorry, the numerator is 4 squared minus 1, and the denominator is 4 squared plus 1. So 16 minus 1 is 15, and 16 plus 1 is 17. And A sub 5 is 5 squared minus 1 over 5 squared plus 1. So 25 minus 1 is 24, and 25 plus 1 is 26, and that reduces to 12 over 13. So our first 5 terms are 0, 3/5, 4/5, 15 over 17, and 12 over 13. Now, it's not as easy to catch a pattern there, so problems like that, they're fun to do. It's not bad. Let's look at a trigonometric one. Number 6 says a sub n equals cosine of n pi over 2. So a sub 1 is cosine of pi over 2, and the cosine of pi over 2 is 0. A sub 2 is the cosine of 2 pi over 2. This means the cosine of pi, and the cosine of pi is negative 1. A sub 3 is the cosine of 3 pi over 2, and that's 0. A sub 4 is the cosine of 4 pi over 2. Well, that means cosine of 2 pi, which is positive 1. And a sub 5 is cosine of 5 pi over 2. And we know that it's come all the way around the unit circle and it's back up to the first quadrant again. So cosine is 0. So this pattern says 0, negative 1, 0, positive 1, 0. Now, we were only supposed to list the first 5 terms. So in the last example, I only listed 5 terms. But these are infinite sequences, so we can put comma, dot, dot, dot at the end. Number 8. Number 8 says a sub n equals negative 1 to the nth power times n over n factorial plus 1. Do you remember n factorial? N factorial is defined as n times n minus 1 times n minus 2 times all the numbers in between times 3 times 2 times 1. So for example, 5 factorial equals 5 times 4 times 3 times 2 times 1. My times dots didn't work, but hopefully you caught that more than not. And then that would be 20 times 6 is 120. So n factorial means I multiply all the integers less than equal to the number. So now let's look at this problem. It says a sub 1 equals negative 1 to the 1 times 1 and 1 factorial plus 1. Negative 1 to the 1 is negative 1 times 1 is negative 1. 1 factorial is 1 plus 1 is 2. Not bad. A sub 2 is, that doesn't go there, negative 1 squared times 2. And on the bottom we have 2 factorial plus 1. So negative 1 squared is positive, so that makes a positive 2 up here. 2 factorial is 2 times 1, which is 2, plus 1 is 3. A sub 3 is negative 1 to the third power times 3. And then we have 3 factorial plus 1. So that's a negative 3 on top. 3 factorial is 3 times 2 times 1, which is 6, plus 1 is 7. A sub 4 is negative 1 to the fourth times 4. And we have 4 factorial plus 1. So this gives me a positive 4 over, let's see, 4 factorial means 4 times 3 times 2 times 1. So 24 plus 1 is 25. By the way, there is a factorial button on your calculator. So if you hit math, it's under the second button. The math, go over to probability, and then there's a factorial button partway down. So a sub 5 would be negative 1 to the fifth times 5 over 5 factorial plus 1. Well, that works out that I did 5 factorial up there. So we have negative 5 over 5 factorial is 120. Let me make sure that's right. 20 times 3 is 60 times 2 is 120 times 1 is 120 plus 1 is 121. So that means the first 5 terms of this sequence are negative 1/2, positive 2/3, negative 3/7, positive 4/25, negative 5 1/21. Now what's interesting about this sequence is what we call an alternating sequence. And that's a term you need to have heard and be familiar with. So this is an alternating sequence. And that term is important because it means the sign changes every time. So you start with a negative or a positive, and the signs alternate. So we start with a negative, and then the second term is positive. Let me highlight this for you. So the first term is negative, the second term is positive, the third term is negative, the fourth term is positive, the fifth term is negative, accordingly. And the thing that makes it be alternating is this -1 to the end right here. That indicates an alternating sequence, and we see those pretty regularly, so that's why I wanted to look at this example. So then let's look at number 10, because it's a different type of problem. So number 10 says a sub 1 is 6, and then it says that a sub n plus 1 equals a sub n over n. This is called a recursive sequence because the sequence is determined based upon the term before it. So a sub 1 equals 6. And then a sub 2, notice that means a sub 1 plus 1, is a sub n, which is the previous one, 6, over n, which is 1. Because this is a sub n plus 1. So we have 6 over 1, which is 6. A sub 3 takes the previous term of 6, and we divide by 2 because n equals 2, and that's 3. Let me back up and do this a different way. Let's say that this one equals a sub 2 over 2, so 6 over 2 is 3. A sub 4, because that's 3 plus 1, is a sub 3 over 3, so we have 3 over 3, which is 1. And a sub 5 is a sub 4 over the number 4, which is 1 over 4. So our first 5 terms are 6, 6, 3, 1, 1/4, ... Let's look at one more of these. Number 12, it says a sub 1 equals 2, a sub 2 equals 1, a sub n plus 1 equals a sub n minus a sub n minus 1. So this is the current term, this is the term before it, and that's the term before that. So a sub 1 is given to be 2, a sub 2 is given to be 1. Let's talk about a sub 3. Now a sub 3 is technically a sub 2 plus 1, right? So keep that in mind. So that means we have a sub 2 minus a sub 2 minus 1, which is a sub 1. So this means a sub 2 is the number 1 minus a sub 1, which is the number 2, and that gives us a -1. So now we're going to find a sub 4. And that's really a sub 3 plus 1. So we have a sub 3 minus a sub 2. Now this right here is not as important. Remember that what we're looking at here is we're looking at the current term. This is the term before it and the term 2 before. So we have the current term, the term before it, and the term before that. So let's go back. A sub 3 then is -1 minus a sub 2, which is 1, and that makes -2. A sub 5 is a sub 4 plus 1. That means I have a sub 4 minus a sub 3. You don't even have to write these when you're writing your answers. A sub 4 is -2 minus a sub 3 of -1. 2 minuses make a plus, so we have -2 plus 1, which is -1. It's an interesting sequence. So the first 5 terms are 2, 1, -1, -2, -1. Another very interesting sequence is the Fibonacci sequence. Now, this is a very famous sequence. It's example 3 in your book. But you don't have an equation for the Fibonacci sequence. It's defined recursively. It's defined as f sub 1 equals 1, and f sub 2 equals 1, and f sub n equals f sub n minus 1 plus f sub n minus 2. So these are our recurring sequence. This is a recurring sequence where n is greater than or equal to 3. So that means we start with 1, and then we have, well, let's put it back in that notation. So f sub 1 is 1, f sub 2 is 1, f sub 3 says I add f sub 2 and f sub 1. So 1 plus 1 is 2. F sub 4 says I add the two previous terms, so I'm going to add the 2 and the 1. So 2 plus 1 is 3. F sub 5 says the two previous terms, 3 plus 2, and that makes 5. F sub 6, I add the two previous terms, 5 plus 3, which makes 8. F sub 7, I add the two previous terms, 8 plus 5 is 13, and so forth. So the Fibonacci sequence, it's named after Leonardo da Pisa, and the Fibonacci sequence is defined as 1, 1, 2, 3, 5, 8, 13, etc. It has lots of applications. He solved a problem on the breeding of rabbits, and that's where this comes from. So there is an exercise. It's not chosen as a homework problem for you, but if you're interested in that, go look up the Fibonacci sequence, named after Leonardo of Pisa. All right, so let's move into part 2 of this exercise. So number 14 says it's a set, it's a sequence, and it's 4, negative 1, 1/4, negative 1/16, 1 over 64, and so forth. Now, your job is to find a sub n. You're trying to find that general term. So if we go back a couple, we're looking for what is this? Now, when we're looking for this general term, it's not always defined based on the previous terms like those two. Up here, it was defined just with the general formula, and that's generally what we're looking for here, is to define your a sub n in terms of itself or numbers or so forth. So let's come back to this problem, and notice the signs first of all. We have plus, minus, plus, minus, plus. This is an alternating sequence, so we need to deal with the fact that the signs change every time. In order for that to happen, I have negative 1 to a power. Now I can't just put n, because on my first term, negative 1 to the 1 power would be negative, so we take away 1, and that balances it out. So now, negative 1 on my first term, negative 1 to the 0 power is even, so it's positive. And then when I have the second term, 2 minus 1 is 1, so negative 1 to the first power is negative. So that handles the alternating signs. Hint, with alternating, you're either going to have negative 1 to the n or negative 1 to the n minus 1. So that's your hint for alternating sequences. Now when I look at this, I see 4 to a power. This is 4, and this is 1/4, and this is 1 over 4 squared, and 1 over 4 to the third. And this is 4 to the 0. But if I look more carefully, I have 4, 1, 1/4, 1/16, and 1 over 64. So on each of these, I'm multiplying by 1/4. So that's the geometric sequence we learned back in pre-calculus. If you don't remember it, I'm going to remind you of it here real quick in just a second. So a geometric sequence says I multiply by a common ratio. And the common ratio is the same number that I multiply by every time. So our common ratio here is 1 over 4. So a geometric sequence says a sub n equals a sub 1 r to the n minus 1. So that's going to be nice and easy. Our a sub 1 is 4. Our r, that's our common ratio of 1/4 to the n minus 1. Now this is also an alternating sequence, so we also have minus 1 to the n minus 1. Now that should go first, so let's put that first. Negative 1 to the n minus 1. Common practice is your negative 1 to a power for your alternating sequence always goes first. And then I'm going to leave this 4 here for just a minute, and we have 1 to any power is still 1, and 4 to the n minus 1. So let's put those on top. Negative 1 to the n minus 1 times 4 over 4 to the n minus 1. Now, this 4 on the top can move to the bottom as 4 to the negative 1 power. You can change the sign of the exponent and put it in the denominator. So now in the numerator, we have negative 1 to the n minus 1. And in the denominator, we have 4 to the n minus 2. When you multiply the 4s, you add the exponents. And here the exponents are negative 1 and n minus 1. So this is your general term right here. You could list the first 5 terms and find them to match the 5 terms listed above. And you should always check your answers accordingly. Look at number 13. It says 1/2, 1/4, 1/6, 1/8, 1/10. Hopefully you see a pattern here because that helps you develop your a sub n. This is not alternating, so I don't have to worry about a negative 1. But I'm going to think about it this way. A sub 1 is 1/2. A sub 2 is 1/4. A sub 3 is 1/6. A sub 4 is 1/8. A sub 5 is 1/10. Sometimes it helps to write them out. So here I see a pattern of 2's. So here I see 2 times 1. And here I see 2 times 2. And here I see 2 times 3. And here I see 2 times 4. And here I see 2 times 5. My times aren't working again. So do you see that the 1's correspond in the first term? And the 2's correspond in the second term? And the 3's correspond in the fourth? And so forth? So that helps me see that a sub n, ... to help us indicate a passage of terms, would be 1 over 2 to the n. Hopefully you see that one pretty easily. Let's look at number 16. It says 5, 8, 11, 14, 17, ... The reason I picked this one is because if you look, to get from here to here, we add 3. And to get from here to here, we add 3. And we add 3. And we add 3. It's called a common difference. This is an arithmetic sequence. If you don't remember these terms, you have 2 main types of sequences in pre-calculus. You have geometric, which means I multiply by a common ratio. And you have arithmetic, which says I add a common difference every time. And so your arithmetic sequence says that a sub n, well, let's build this without knowing the arithmetic sequence and then come back. So I start with 5. I start with a sub 1 equals 5. And then a sub 2 equals 5 plus 3. And then a sub 3 equals 11, which is technically 5 plus 3 plus 3, right? And a sub 4 is 14, which is 5 plus 3 plus 3 plus 3. Are you seeing the pattern I'm trying to build for you here? So what we can do is we know that this is 5, and this is 5 plus 3, and this is 5 plus 2 times 3, and this is 5 plus 3 times 3. So you don't have to build the formula. You can think about what it is. A sub n equals 5 plus, now notice the 2, it's 1 less than it was before. So we're going to say 3 times n minus 1. Because this value right here is 1 less than n every time, because there's an understood 1 here. So here we could write in an understood 0, because 0 times 3 is 3, so that doesn't affect it. So we get that far, but you have to simplify and combine like terms. So we have 5 plus 3n minus 3, and 5 minus 3 is 2, plus 3n. So a sub n equals 2 plus 3n. Now you could check those answers. If you remember your arithmetic sequence, it says a sub n equals a sub 1 plus n minus 1 times d. D is your common difference. So we know that a sub n equals a sub 1, in this case is 5. And we leave the n minus 1, and our d is 3. Our difference is 3. And that puts us right back down here. So we know a sub n is 5 plus 3n minus 3. So a sub n is 2 plus 3n. So you can get the same answer whether you know your arithmetic sequence or if you look at the pattern developing in the number. Let's look at one more of these, number 18, and then we'll probably wrap up this video for the next one. Number 18 says 1, 0, negative 1, 0, 1, 0, negative 1, 0, dot, dot, dot. Now they gave us enough to determine a pattern. So let's look at this pattern. There's not anything you can multiply to come up with that. There's not anything you can add, because from here to here you can take away 1. So you could add negative 1 and add negative 1, but when you add negative 1 here, it fails. But if you think about it, what values give us 1, 0, negative 1, 0? Hopefully you're thinking on this line with me. Let's think trigonometry. So trigonometry sine goes like this, but it starts at 0. And then at pi over 2, it goes up to 1. So we could start it here, because then it goes down to 0 and down to negative 1, and so forth. So our sine graph, if we start at a shift, that would meet the requirements. But let's look at a cosine graph. A cosine graph goes like this, and it continues. So at 0, the y value is 1. At pi over 2, the y value is 0. At pi, the y is negative 1. At 3 pi over 2, the y value is 0. And then back at pi, the y value is up to 1. So that covers the first 5 terms. And it's periodic, so it continues along that pattern. So when we try to come up with a general term, if you think about cosine, this is y equals cosine x. So a sub n equals cosine. Now we don't just want to say n. We want to look at this as this is 0, and this is 1 pi over 2, and the next one is 2 pi over 2, and then we have 3 pi over 2, and 4 pi over 2, and 5 pi over 2. So you could map them out and say that 0 gives me a y value of 1. 1 pi over 2 gives me a y value of 0. And so forth. So we could call this n times pi over 2. And that's our general term here. I think we might have time for one more. Look at this problem. It says 3/5, negative 4 over 25, 5 over 125, negative 6 over 625, and 7 over 3125. Continued, because it's an infinite sequence. So if you look at it, my first term is 3 over 5. Look at the top. First of all, it's alternating. So an alternating sequence says I have negative 1 to some power. And if I say the n power, then my first term should be negative, and that's not correct. So we're going to do n minus 1. Now look at the top. It says 3, 4, 5, 6, 7. So a sub 1 is 3 over 5. And a sub 2 is negative 4 over 5. We've already dealt with the negative. And a sub 3 is 5 over 125. Notice they're each going up by 1. A sub 4 is negative 6 over 625. So this is 1 plus 2, and this is 2 plus 2, and this is 3 plus 2. So look at the fact that that's n plus 2 on each of these. 1 plus 2, 2 plus 2, 3 plus 2, still true here, 4 plus 2. Down here I have 5 to the first, so that's 5 to the n. 5 to the second, still 5 to the n. 5 to the third, still 5 to the n. So we have a sub n equals negative 1 to the n minus 1 times n plus 2 over 5 to the n. Thank you.